Okay, so yesterday we had a discussion on various operations of binary search tree. Uh, we have seen how to create a binary search tree, how to insert a node into a binary search tree, then how to traverse a binary search tree in order, pre-order, and post-order traversal. Then how to search a node into a binary search tree. And also we had a discussion that how to delete a given node from a binary search tree. Okay. So today we'll be talking about the applications of binary search tree, or rather the applications of a binary tree. So these things we have already seen in order, pre-order, and post-order traversals of a binary search tree. Then we have also taken an example of a binary tree with non-numerical data. There also we have seen different traversal techniques, and we have also seen that how to create a binary tree from a given traversal sequences. So if a in order and pre-order is given to you, then you can recreate or reconstruct a binary tree. If a in order post order is given to you, then you can recreate or reconstruct a binary tree. So that also we have seen. Now the next, this deletion also we have seen. So the next topic is basically applications of binary tree. So basically we'll be learning about two important applications of binary tree. The first application is the expression trees, that how a binary tree is used in expression tree. What do you mean by expression tree? How to create a expression tree, and what happens when you traverse the expression tree in different traversal techniques. Okay, so that we'll see. And then the second important application of binary tree is Huffman encoding. So Huffman encoding is basically a compression technique where we try to reduce the space requirement of the data without changing the data. So without affecting the integrity of the data, without changing the original data, we try to reduce the space requirement. So that is called compression. So one of the compression techniques is Huffman encoding. Compression is also called as encoding. So one of the compression techniques is Huffman encoding, and this is the application of binary tree. So we'll see that how to use a binary tree, how to create a Huffman tree using some concept, and then how to make use of that Huffman tree. Okay. So first we'll start with the first application, that is expression tree. So what do you mean by an expression tree? So a simple understanding of an expression tree is this. Expression tree is a binary tree in which each internal node corresponds to operator and each leaf node corresponds to operand. It means that from the name itself we can understand it is a tree of an expression. Expression tree. So it is a tree of an expression. And when you think about an expression, so in an expression, so basically we are talking about a mathematical expression. So in a mathematical expression, you have two possibilities. Either you have an operand or you have a operator. You have an operand or you have a operator. So when you form or when you create an expression tree, so all the internal nodes are your operators, and all the operands are basically the leaf nodes. So the leaf nodes or the terminal nodes are the operands. So all the operands will be appearing in the leaf nodes or in the terminal nodes, and all operators would be appearing or would be representing your internal nodes or the non-leaf nodes. Okay, a non-leaf node or the internal node is a node which has at least one child, and a leaf node is a node which always have a zero child, no child. So that is called as a leaf node. So all leaf nodes will be the operands, and all non-leaf nodes or the internal nodes will be operators in an expression tree. Okay. So now let's see that when we talk about an expression tree, basically how to create an expression tree. That is the first question, a very important question. Once you create an expression tree, then you can do so many things out of that created expression tree that we will see. But before that, we need to understand that how to create or how to form an expression. So basically, there is an algorithm. There are some simple steps that we need to follow to create an expression tree. And for creating an expression tree, as I said you, there is an algorithm. The algorithm to create an expression tree is there. So while creating an expression tree or while following the algorithm or the steps to create an expression tree, we need an expression. I repeat, we need an expression to create an expression tree. If you do not have any expression, you cannot create an expression tree. So basically, an expression tree represents an expression. So we need an expression to create or to form tree, a binary tree. Okay. Now, this expression, which we are taking as an input for the algorithm or for the program to create an expression tree. So this expression can be either in the form of infix expression or can be either in the form of postfix expression. When it is in the form of postfix expression, so the creation is quite simple and straightforward. When it is in the form of infix expression, so the creation is little tricky. Okay, so you can create it. So what we will do, we will take an input in the form of a postfix expression and we'll create an expression tree. So basically the input for an algorithm to create an expression tree in this case is a postfix expression. I repeat, a postfix expression will become an input for this algorithm or for a function to create an expression tree. Okay, so you have a postfix expression with you, and now you need to follow the algorithm. So the first step in the algorithm is to read or scan the given postfix expression from left to right. So whatever is the postfix expression, AB plus or AB into C plus. So whatever is the postfix expression, we will be reading or will be scanning the postfix expression from left to right. Okay. Yeah, you can just try to recollect your algorithm for infix to postfix conversion. Okay, so you used to just scan or read the infix expression from left to right, and then you try to see what is an encountered symbol. Encountered symbol is an operator or an operand, and so on. So likewise, we'll be doing in the algorithm to create an expression tree. We'll be reading the given postfix expression from left to right. So if the postfix expression is, for example, AB plus C minus, so we'll be reading it from left. So the first symbol we are going to encounter is A, and then B, then plus, then C, then minus. Okay. So likewise, we'll be reading it from left to right. This is the first step. Second step, if an operator, if an operand is encountered, then push it onto the stack. A very simple step. What we need to do? There are two possibilities. We are reading a postfix expression, and if you recollect what is a postfix expression, so basically a postfix expression is an expression which has only two things: operators and operands. That's all. It doesn't have those brackets, left para and right para. So the postfix expression is going to have only two things. Either it is going to have an operator or means the symbol which you are going to encounter while reading from a postfix expression. So it is going to be an operator or it is going to be an operand. Okay, only two possibilities. So for the first possibility, if it is an operand, then simply push it onto the stack. If it is an operand, then simply push it onto the stack. Second possibility, if an operator. So if an operator is encountered, then what we need to do, we need to make this operator as the root node of a subtree. Okay, we are forming a subtree now. So if an operator is encountered, then make it as a root node. So operator becomes a root node of a subtree, and then pop from a stack.
pop from a stack and make it a right child of this root node. Okay, I repeat. What we need to do when an operator is encountered, make it as a root node of a subtree. Just we are forming a subtree now. Pop from the stack, whatever you pop from stack, that will become the right child of this subtree, of this root node. Again, pop from stack, whatever you pop, that will become the left child of this root node. And now subtree has been formed. You need to push this subtree onto the stack again. So push the subtree on the stack. I repeat this step. This is simple. It appears little tricky, but it is simple. If an operator is encountered, okay, then this operator, the encountered operator, a node will be made out of this encountered operator. That node will become the root node of a subtree which we are just preparing now. Okay, so the encountered operator becomes the root node of the subtree. Then we'll perform one pop operation. Whatever we pop from the top of stack, that becomes the right child of this root node. Okay. We again pop from the top of stack. Whatever we pop now, that becomes the left child. That becomes the left child of this root node. And now this subtree, just formed subtree, just created subtree, will be pushed onto the stack. Okay. Now, technically, and from implementation point of view, when we say that an operator operand is pushed onto the stack, or we say the subtree is pushed onto the stack, so basically we are talking about pointers. For each of this operand and operator, basically a node would be created because it's a tree. Okay, operators are the internal nodes and operands are the leaf nodes. So they are nodes. So node will be created for each encountered symbol. For every symbol, a node would be created. So when an operand is encountered, so a node is created for that operand, and then that node is pushed onto the stack. From implementation point of view, from programming point of view, basically pushing a node means pushing a pointer to that node onto the stack. Please hear carefully. From implementation point of view, from programming point of view, when I say a node is pushed onto the stack, so I mean to say a pointer to that node is pushed onto the stack. So basically my stack is implemented as an array, and that array is not an array of integers, it's an array of pointers. And pointers to what? Pointers to node. Okay. So basically when I say a node is pushed onto the stack, I mean to say a pointer to that node is pushed onto the stack. Likewise, in the third step, if an operator is encountered, we create a node for this operator. That node becomes a root node. We make one pop operation. We make it, whatever we pop, basically we pop a node from the stack. So we make it as the right child. We perform one more pop. We make it as a left child of this root node. And then this subtree is pushed onto the stack. So it simply means that the pointer to the root of this subtree is pushed onto the stack. I repeat, from implementation point of view, it simply means that the pointer to the root node of this subtree is pushed onto the stack. So on paper, when we solve, so basically we show that a subtree is pushed onto the stack while showing it. But from implementation point of view, you will be pushing a pointer to the node, to the root node of this subtree. Okay, we'll see that at the time of implementation. So right now, keep it simple. What we are pushing a subtree onto the stack. Fourth step, repeat from step 1 until the postfix expression is exhausted. Repeat from step 1 until the postfix expression is exhausted. So again, you will be going to step 1, you will be reading the next symbol, you will be checking whether it's an operator or an operand. If it is an operand, then push it onto the stack. If it is an operator, then make it as a root, pop, make it as a right child, pop, make it as a left child, and push this entire subtree onto the stack. Okay. then again go back, again read the next symbol from the postfix expression. Keep on doing this. Keep on doing this until your postfix expression is exhausted. The moment your postfix expression is exhausted, it is completed. Okay, there is no more symbol to read from the postfix string or the postfix expression. Then the last step is pop the expression tree or the root of the expression tree from the stack. So once your postfix expression is completely exhausted, when it is done, so whatever you have into the stack is basically your expression tree. So just pop your expression tree from the stack. And technically we mean to say pop a root node of the entire expression tree from the stack. Pop the root node of an entire expression tree from the stack. We mean to say that. Fine. Now, let's take an example. Whether these steps are understood to all, any query into this? I think this is quite simple, straightforward. As far as your on-paper solution is concerned, it is very simple. It is very simple, on-paper solution. When we talk about on-system solutions, when we talk about implementation, it is little tweak. Only you need to play with the pointers, that's all. When we see the implementation, then inshallah you will come to understand it. So the next step is to create an expression tree. So we'll follow this algorithm, these steps, and we will try to create an expression tree for this given example. Okay. So the given example is basically a postfix expression. The input to the algorithm is a postfix expression, and in this case, this is a specific. You can say postfix expression which you need to use to create an expression. So the input is A, B plus E, F star, E star minus. Okay. What can be done? You can also start creating it parallelly, and I will also start doing. Okay. So now what I do, start solving it. First, let me stop my camera. Just hold on, please. So the input is AB plus EF star minus. Okay. Now we'll start scanning this given infix postfix expression from left to right. So when we start scanning it, what we read first, we read A. So A is the first symbol which is encountered. So when we read A, we know A is an operand. Okay. So in the first step, A is encountered. So A is encountered, and we know that A is operand. So the algorithm says that the operand should be pushed onto the stack. So I just draw a stack and I make a node for A and I push A onto the stack. That's why I'm putting it on in a circle, okay? Because A is a node. Then the second step, B is encountered, and B is also an operand. So what is to be done? You already have A in your stack, and then on top of a node B will go. Okay. So now you have two things in your stack, and then the third step. In the third step, what we can see, plus is encountered. Fine. Now plus is encountered. Plus is an operator. What we need to do, we need to make it as a root node of my subtree. Pop from the top of stack. So when you pop from the top of stack, so what is popped? We can understand that when we pop from the top of stack, just a minute. So when we pop from the top of stack, so we are going to pop this B. Okay. So B is popped, and that B becomes the right child. So the first pop will give me B, that becomes the right child. And then when I pop it for the second time, so we can see here that A is popped. Okay. When A is popped, so now this A becomes a left child of this subtree. And then this subtree is pushed onto the stack. Okay. So now when I draw my stack, so basically what I am getting, B has been popped out, A has been popped out. So I do not have anything onto the stack. My stack is empty, and into my empty stack, I'm going to push this entire subtree. Okay. From implementation point of view, I repeat, it will be only the pointer to the root node of this subtree. So pointer to plus. But for the paper presentation, we'll be pushing this entire subtree. So basically, I will be drawing this subtree again here. And I am saying that this is a part of my stack. Okay. So basically, this subtree is pushed onto the stack. And then I have the fourth step. What is fourth step? What is encountered? E is encountered. What is E? E is an operand, and it has to be pushed onto the stack. So I do not redraw the stack here. What I do, I push onto this stack itself. So above this subtree, there will be a node E. Okay, inside my stack. Fine. Then the fifth step. What is encountered after E? After E, I have F. So F is also an operand. So this will also be pushed onto the stack. So above E, I am going to have F in my stack. Okay. Then my sixth step. So after F, I have now star. So star is encountered. What is star? It is an operand. Now, when an operand is encountered, sorry, it is an operator. Sorry, it is an operator. So when an operator is encountered, what we need to do? We need to make it as a root node of a subtree. I will be performing first pop. So when I perform the first pop, so I will be getting this F out of my stack, and this F will become the right child of this. So F becomes the right child. Then I will be doing one more pop. When I do one more pop, so I will be popping this E, node E, and then node E becomes the left child of this subtree, and then I will be pushing this onto the stack. Okay, so when we push this onto the stack, now see here carefully what's happening. This has been popped, this has been popped. Okay, so now in our stack, what we have only this. We have only this, and now above this, that subtree will be pushed. Okay, so that subtree is having the root node as star, right child as F, and left child as E. Okay, and that comes on top of my stack. So this is the current status of my stack. Okay, and now in the seventh step, after star, you have G. Now G is encountered, and G is what? G is operand. So push it onto the stack. So let me clear this. Fine. So push it onto the stack. So what do we have? We have a node having a value G, and now this node comes on the top of my stack. So this is the stack with us, and now after the G, we have the next step, step number 8, and after G, you have star. So star is encountered. We know that star is an operator, and what to do when an operator is encountered? Make it as the root node of the subtree. Star becomes the root node, and then pop from the top of stack. So when we pop from the top of stack, so we get G. So this G is popped, and this will become what? The right child of my subtree. So G becomes the right child of my subtree. Then we pop once more, and now this time when we pop, so we get this subtree. Okay, we are going to get a subtree having star, E, and F. Star, E, and F. So that will become the left child of this subtree. So on the left of this, you have another subtree, star, E, and F. Okay, so this is now the subtree which has been created, and now this was popped from the stack. This was also popped from the stack. So these things aren't there in your stack. Only you have this node, this subtree in the stack, and now this newly subtree will also be pushed onto the stack. The step is what? This newly subtree should be pushed onto the stack. So now
we'll be pushing this subtree onto the stack. So when we push that subtree onto the stack, so we have this. Star is there. And here you have E. And here you have F. And then this side, what you have? T. And then you have star over here. Like this. Okay. So this subtree is now pushed onto the stack. Fine. And then your step number 9. And then finally we encounter the last symbol, which is minus. The last symbol is minus. This minus is an operator. So again, what we do, we create a node for this operator and we make this operator the root node. We perform one pop operation and that will become the right child. So when you perform the pop operation, you are going to get this. Okay. So this subtree will be popped. So this becomes the right child. Okay. This subtree is popped and it becomes the right child. So what you have a star over here. And then you again have a star. Then you have your E. Here you have F. Then you have G. Okay. So this becomes the right child. And then we perform one more pop. And when you perform one more pop, so this time we'll be getting this. So plus AB. This becomes the left child plus AB. So I come to this side. Plus A and then B. Okay. And then finally what we'll be doing, we will be pushing this tree, this tree into the stack. And then we go for the next symbol. And when we try to read the next symbol, so we do not have anything over here. So our postfix expression has been exhausted. And this is the final tree which we are getting out of this given example. So this tree is an expression tree for the given example. I repeat, this is the final expression tree for the given example. Okay. And now, what you can see over here, that in this specific example, in this expression tree, this is the expression tree which we are getting out of a given example. If you do a in-order traversal of this expression tree, you will be getting a infix expression. If you do a reorder traversal of this expression tree, you will get the prefix expression. And likewise, if you do the post-order traversal of this expression tree, so you will get the postfix expression. Okay. So let me do the in-order traversal. So when I do the in-order traversal, so what I get when we do the in-order traversal of this expression tree, so basically we'll be getting what? We'll be getting first A, then we will be getting plus, and then B, and then minus, and then E, then star, then F, and then star, and then G. So this is going to be the infix expression of this expression tree, which we get out of in-order traversal. When we do the reorder traversal, so what we get, the first is the root node minus. So for the pre-order traversal, we'll be getting
For the pre-order traversal, you'll be getting minus and then plus and then AB and then into and then again into, then E, then F, and then finally G. This is the pre-order traversal. And when I go for the post-order traversal, so what we'll be getting? We'll be getting first A, and then B, then plus, and then E, then F, then star, then D, then star, and then finally the root node is minus. Okay. So this is the infix expression which we are getting out of in-order traversal. Then the prefix expression which we get out of pre-order traversal, and finally the postfix expression which we get out of post-order traversal. Okay. So the expression tree created out of a given postfix expression with the help of stack, and then when we do the traversal of this expression tree, then we go get all the three expressions. In-order traversal will give you infix, pre-order traversal will give you prefix, and the post-order traversal will give you postfix. Post-order traversal will give you the postfix expression. Okay, so this is how with the help of expression tree we can get any expression. Once you have the expression tree, then you can get all the three type of expression just by traversing that expression. Okay. The only important thing is to create the expressions tree correctly from the given postfix expression, and that creation is also quite straightforward and simple. Now, what I do is this understood to all. Thank you. Just a minute. So we are coming back to our main presentation. I think this is coming back to our main screen. And this is session 34. And, this is the implementation of expression tree, and we are creating an expression tree using the given postfix expression. Okay, So what I will be doing now, we are running out of time. I cannot explain you the code for it, but the code is quite simple and straightforward if you understand the language properly. So if you know English and if you remember how do we create a binary tree and basically how do we create a binary search tree. So this is also quite straightforward and simple. Since this is also an application of stack, so apart from the structure for the binary search tree, let me call it binary tree rather than binary search tree. Apart from this structure, we also have the stack structure. And inside this stack structure, now if you see carefully, and this is a stack using arrays. And so the top variable is the integer type variable, but this array is an array of pointers. Is an array of pointers of type BST. And this BST is not nothing but type defined of structure BS2. Okay, so BST is our you can say structure BS3. So in short, this array is nothing but an array of pointers to structure BS2. This is an array of pointers. Array of pointers. I repeat, array of pointers, and each of these pointers is a pointer to a structure BS2. Okay. Each of these pointers is a pointer to a structure BS2. Okay. Keeping that in mind, and the way we used to have a program for all our implementation, trying to keep the program as modular as possible, as general as possible. So same way we are keeping this program. So we'll have a discussion on this in the next session. Time is running now. So I will provide you a code for this. Any query meanwhile?